So now we're going to take a look at another sample problem involving heat conduction. This time we have a case where heat flows over a non-uniform cross-section area. So consider this following setup. We have a cylinder with a hollow core inside. And so the cylinder has an inner surface and an outer surface. Now, the inner surface has radius A, and the outer surface has radius B. Suppose the inner surface is at higher temperature T sub A than the temperature on the outer surface, which is T sub B. Can you determine the rate at which heat flows in the cylinder? Okay, looking for the thermal power P. Now, again, as the heat flows out, it encounters a non-uniform cross-section area. You can see from the top view in this diagram here. Okay, in this diagram here, the top view. So I have heat flowing radially outwards like this. Hold on. Radially outwards like this, right? From the inner surface to the outer surface. So how does one find the rate at which heat flows over a non-uniform cross-section? Now, we don't know how to do that. We only know how to figure out the heat flowing through a uniform cross-section area. And since the area grows as the heat flows outwards, we are forced to divide the segment, divide this route along which heat travels into a variety of segments. And in this blue shaded region, you have a thin cylinder. Okay, a thin cylinder between radius R and then R plus dr, so the thickness is dr. Now, consider the heat flowing over this thin region of the cylinder. Because dr is very small, you can pretty much assume that the cross-section area does not change as heat flows from the inner to the outer side of this very thin cylindrical shell of radius R and thickness dr. Okay, so since it's a uniform cross-section area, we're able to calculate the rate at which heat flows. There's a formula for that. So that is P equals to K times the area, and then you have dt dr. Okay, I cannot use delta T over delta R because we're looking at a very thin segment of thickness dr only. So the A is the area of this blue shaded cylinder. We're talking about a side area, okay? That is 2 pi R times the length, which is L, right? That's the cross-section area. And then you time dt over dr. Okay, again, we're looking for P, right? The problem is we don't know what dt over dr is. Can we assume it to be a constant? Well, that is not necessarily true because the area changes, okay? The area actually changes. And the problem here is that the area can change, dt dr can change, but P cannot. Why? Because P is the rate at which heat flows through a certain cross-section area. And it has to stay the same as heat flows across any part of this cross-section area of the cylinder. If that is not the case, let's say you have a situation where more heat flows inward and less amount of heat flows outward during the same time. The problem with that is that for this region, you know, between the here and there, you're going to have a net influx of heat, which means the temperature will rise. And that is not happening because we're looking at a case where the temperature stays the same at a given point. Okay, it's a steady state. So therefore, P is not a function of R. I don't know what P is. That's what I try to find out. But at least I know P is not a function of R. It's a constant. So how do we find that constant? Well, there's a condition that I haven't used yet, and that is the inner temperature. The inner surface has a temperature of TA. The outer surface temperature of TB, okay, that I have not used. So let me label that. The temperature here is TA, the temperature there is TB. So how do I take advantage of that? Well, what I can do is I can solve for dt, okay? I can solve for dt from the formula above. Then I can integrate over dt between the inner and outer radii, and then I get delta T, right? and delta T should be equal to TB minus TA. That's how you utilize this condition. Okay, so let's do that. Let's solve for dt. So dt equals to, you have P on the other side, and then 2 pi KL R dr, right? Now, integrate over both sides. Okay, here the temperature went from TA to TB, while the radius went from A to B, right? The left-hand side, the integral is TB minus TA. And the right-hand side, remember P is independent of R, so it's a constant, which I can take out. And other constants, 2 pi KL, all these are constants. You're left with the natural log of R, 1 over R dl, which is the natural log of R. So one more step here. I can now finish this integral, right? P over 2 pi KL, natural log of B over A, right? And this allows me to find P. So P, I can solve for P now. It is equal to TB minus TA times 2 pi KL divided by the natural log of B over A. Okay, so this is my result. And so what's the trick that I use here? Well, I divided this cross-section into consecutive thin shells and looked at the heat rate flowing through one of those very thin shells. And the reason why, again, I did that is because that's how I solved the problem of non-uniform cross-section area. Over a very thin shell of thickness dr, the cross-section area is pretty much uniform. So I apply this formula for uniform cross-section. I find P equals this. And then I encounter dt over dr. And the way I deal with that is I realize P is uniform. It's not a function of R. And I just solve for dt and integrate between inner and outer radii of the cylinder. And then I utilize the condition that temperatures are given at the two borders, TA and TB. Okay, so that's how I did that. Now, you can imagine if the thickness, the overall thickness, which is B minus A, if this quantity is a lot less than A and B, then look at a very thin shell, right? For a very thin shell, the cross-section area is pretty much uniform, right? For uniform cross-section, I know how to calculate the thermal power. So if, I can check that, okay, if B minus A, that's the thickness, is a lot less than either A or B, okay? So let's say we divide it by A, is a lot less than 1, okay? So that's very thin shell. For very thin shell, it's essentially uniform in cross-section area, and then P should become what? Well, I use the formula for uniform thickness, right? It's Ka delta T over delta R for uniform cross-section. And I know what A is. A is 2 pi AL or 2 pi BL. Look, A and B are not that different, okay? 2 pi A times L, that's the area of the cross-section. Okay. And then you have delta T over delta R. Delta T is the temperature difference between the inner and outer shell, and that is TB minus TA, divided by delta R, which is the thickness, which is B minus A. Okay, so that's what we expect when the shell is very thin. Now, on the other hand, we have this general expression, right, that's highlighted, right? That's valid for any thickness of the shell, whether thin or thick. But mathematically, can this general expression reduce to this special case of thin shell when B is pretty close to A? Well, you look at the general expression, there's a natural log function, which is missing in this special case of thin shell. But a natural log function, okay, I have natural log of B over A. the natural log function can actually be approximated when the argument is pretty close to 1. Okay, the argument here is b over a, but since b and a are pretty close to each other for a thin shell, we can look at, when we look at the case where the shell is very thin, mathematically, I can write this as natural log of a plus delta r over a. Why not? Because b is a plus delta r, delta being the thickness of the shell, and thickness is very close to, the thickness is very close to 0. Let's see what happens. So this is natural log of 1 plus delta r over a. And delta r is a lot less than a, right? So this is roughly equal to what? 1 plus delta r over a. Actually, just delta over a, I'm sorry. Just, there's no 1 plus. Delta r over a. If you don't recall where that formula comes from, here's the little math tip here. Natural log of 1 plus x is roughly equal to x if the absolute value of x is a lot less than 1. Okay, you recall that mathematically. Now, in our case, we have this x, which is equal to delta a over r. So x equals delta a over r in our case, which is indeed a lot less than 1 for a thin shell, right? So the denominator can be replaced by delta a over r, and then this p, this general expression, becomes what? Tb minus Ta over times 2 pi Kl over, instead of natural log of b over a, I can just replace with delta r over a. Delta r is b minus a over a. I flip the a over, I get it here. Okay, now you compare these two expressions. You compare these two expressions. Don't you get the same thing? Right? It's exactly the same thing. 2 pi Kal times delta Tb minus Ta over b minus a. So indeed, our general expression reduces to the special case of a thin shell with nearly uniform cross-section area. Okay, so this is an example of heat flowing through a non-uniform cross-section, just like the previous example when you have a multi-layered configuration. The basic idea is that the thermal power P flowing through every portion on its way from the hot surface to the cold surface must be the same in order to prevent any heat, any energy buildup or energy loss, which will result in a change of temperature over time, which we know doesn't happen in a steady state. Okay, so this was our discussion about conduction of heat. Now we can talk briefly about convection and radiation, the other two modes of thermal, of energy transfer through heat. The convection of heat differs from the conduction of heat in the sense that in a case of convection, you actually have particles moving, flowing in the medium. And as they move, they can exchange their energy with the surrounding, okay? In this case, you have boiling water in a stove, right? And near the bottom, the temperature, that's near the flame, near the bottom of the stove, the temperature is high, and the water in this region is hotter than the region near the top. And then instead of just gradually decreasing the temperature to the top and allowing heat to conduct from the bottom of the water to the top, when the temperature variation is high enough, is great enough between the bottom and the top layer, water can actually flow, okay? Water can actually flow between the top and bottom layer, forming a loop that you can see in this diagram, right? So you have a loop like this, you have a loop like this, and a loop like this. So the water starts from the bottom when its temperature is high, and it flows to the top, and that's where the surrounding is cooler. So it gives up its heat, and then becomes cooler again, then come back near the bottom, gets heated up again, and the cycle repeats. So this mode of heat transfer involves actual motion of particles, in this case, water. So this can only happen in a fluid such as gas or liquid. It cannot happen in a solid. Okay, And convection plays a major role in weather patterns. You know, when the sun shines upon the surface of the Earth, it creates a temperature difference at different layers of the atmosphere. Okay, in general, the part near the surface of the Earth is warmer, and higher you go, the cooler it gets. So there's a temperature gradient, and when that gradient is high enough, it can produce a motion, a movement of the air. Okay, it's just like the water current flowing inside this kettle, and so the warmer air would rise, okay, to a region where the surrounding is cooler, and it will give up its heat, and then it will just will just sink. Warmer air is not as dense as cooler air, right? Because of thermal expansion. It's not as dense, therefore, it will tend to move up because of the buoyancy effect. So it's natural to have this flow of air forming a loop that has major consequence in weather patterns. And there are many other examples of convection. But we can only talk about qualitatively. It's much harder to study quantitatively than conduction. Now, the third mode of heat transfer is also extremely important. That is called radiation. Radiation. Okay, radiation is the mode of heat transfer that can happen over vacuum. There's no touching. There's no particle involved at all. Okay, consider an object at a certain surface temperature. Okay, let me draw an object of an arbitrary shape. Okay, I have this object of arbitrary shape, and it's got a certain surface area A, and the temperature of the surface is T. I don't care the temperature inside, the temperature of the surface is T. As long as T is not at absolute zero, okay, as long as it has certain finite temperature, it's going to radiate electromagnetic wave. It will radiate electromagnetic wave. Every object whose surface temperature is not absolute zero will radiate electromagnetic wave. Okay, the energy given out that way is called radiation. It's basically an electromagnetic radiation. And in chapter 39, we will examine this problem in more detail. We'll produce important results, such as the Stefan-Boltzmann law. You will see. It's actually called Stefan's law that you will see below. Right. This is so important because, as you know, the energy from the sun, that's how it reaches us, right? I mean, there is vast vacuum separating us and the sun. So certainly there's no conduction possible, and there's no convection possible. And the only way for the Earth to receive energy from the sun is through this mode, radiation. Okay, so how much radiation takes place? What is the power of the radiation over an object whose surface area is A, whose surface temperature is T? And it turns out that there is a law governing that. Again, you will see that in chapter 39. Okay, this law is called Stefan's law. Okay, so what does this law say? Stefan's law. It says that the thermal power equals to a constant sigma, okay, times the area, the surface area of the object, times another constant E, and then times the surface temperature T in absolute Kelvin scale to the power 4. Okay? That's what Stefan's law says. This will be derived in chapter 39. But let's first take a look at what these symbols mean. Sigma is a constant. You can find this value experimentally, but we can also derive it theoretically based on our knowledge of quantum mechanics in chapter 39. It's called Stefan's constant, and the value is given. Okay? In the textbook, you can find this value in the textbook. I'm gonna write that down for you now. About 5.7 to 2 sig figures times 10 to the -8 in SI unit. Okay, so what's the SI unit? What is the SI unit of this constant? We'll just balance both sides. So the left side has a watt, right? That's thermal power, right? Watt. And then you the right hand side with the area. E is just a number. There is no unit for E. So area squared, which is meters squared, right? And then you have Kelvin to the power 4 because of the balance K to the power 4. Okay, that is the Stefan constant. Okay, and then A again is the surface area. T is the surface temperature in Kelvin scale. E is a number. There's no unit called emissivity. Okay, emissivity. That's E. What is E equal to? It's a number between 0 and 1. Zero means there is no power emitted whatsoever. 1 means this is a what's called black body. Okay, what's a black body? A black body is such an object that when you shine, when you throw whatever energy at it, okay, you radiate energy towards it, it's going to absorb 100% of the energy that you give to it. It's a perfect absorber. That's called a black body. If E equals 0, then that means it receives no energy through radiation. It reflects everything you throw at it. Okay, that's what's called a white body. These are two extreme cases. In the real world, E is a number anywhere between 0 and 1, and that's called a gray body. So, every real world object is a gray body, somewhere between perfect white body and perfect black body. Okay, so that's the definition of these numbers. Now we're going to use, we're going to take a look at an important real life example, and that's treating the sun as a nearly ideal black body. Can we use this formula to find the total power output of the sun, leading to what's called a solar constant? Okay, solar constant. One of the most important numbers and most important constants that help determine our future. So before we do that, I also want to talk a little bit about so-called primary wavelengths of the radiation. Primary wavelength of radiation. Every object whose surface temperature is at T will radiate, but what kind of wave do they radiate? We know it's electromagnetic wave, right? What kind of wavelengths? It turns out it's a variety of wavelengths. It's not one given wavelength. But depending on the surface temperature, the primary radiation, which is radiation with the strongest intensity, has a certain wavelength, okay? That turns out is dependent upon the surface temperature in such a way that the primary wavelength, lambda radiated, lambda p, is inversely proportional to temperature of the surface. Okay, that means the higher the surface temperature, the shorter the wavelengths. Okay, and there's a constant which would turn this into an equal sign, and then you will learn that in chapter 39. But I can tell you from what our daily experience teaches us. If you look at the sun, okay, the sun radiates all kinds of electromagnetic waves, but the primary radiation is in visible light rays. That's why the sun is visible. Okay, not only so, it radiates in a certain primary color, which is yellow. The sun looks yellow. And it's because the surface temperature of the sun is such that the primary radiation, the strongest radiation, comes from the yellow color of the visible light spectrum. Okay. Whereas if you look at a daily, objects around us, such as a desk, a book, a tree, and our body, these are we're talking about near room temperature, right? The temperature is much lower than the surface temperature of the sun, right? Surface temperature of the sun is about 5,500 degrees Celsius, okay? Or about 5,800 Kelvin. But at the room temperature, we're talking about 300 Kelvin, right? 20, 30 degrees, about 300 Kelvin. An object whose surface temperature is several hundred Kelvin, it does not radiate primarily in visible light. No, the frequency, the dominant frequency, dominant wavelengths is actually longer. Remember, the lower the surface temperature, the longer the wavelengths, right? So it gets lower from the yellow color, the wavelength of the yellow color, and gets longer, it goes into infrared range. That is why every object at room temperature radiates primarily in infrared, okay? The human body produces warmth around you is because we radiate in infrared, okay? Along with every object at room temperature. All right, now let's go back to the Stefan's law, and let's use that, assuming the Earth, assuming the sun to be a perfect black body. Let's calculate the total power output of the sun to see if it actually works, if the formula actually works. Now you may wonder, how come the sun is a perfect black body? I mean, it doesn't look black, right? Well, here's the thing. Here, black doesn't mean it's black literally. Okay, what it means, again, is that whatever radiation you shine upon the sun, it's going to capture it. It doesn't reflect anything. But the thing is, if you're a black body and whatever radiation you get, you absorb it. If that is the only thing you do, you only absorb radiation, then your temperature is going to go up because you're going to get energy. Right? You just get energy from the surrounding. But if the temperature doesn't change, that means it has achieved a balance, which means a black body not only receives energy, it also has to radiate energy out to reach a balance. And so the amount of radiation that a black body radiates per second, that's the thermal power, that is given by the Stefan's law, okay? Everything radiates, but for a black body, this number E, the emissivity, equals 1, okay? The more it absorbs, the more it radiates because you have to achieve a balance. Okay, so for the sun, let's look at some numbers. We know what sigma is, right? And the area of the sun, the surface area of the sun, you can easily Google that, okay? So for the sun. Okay, why don't I just write down these numbers? Okay, let me write down these numbers. So for the sun, the surface area is 6.07 times 10 to the 18 meters squared, and the surface temperature is 5,778 Kelvin. Again, that's about 5,500 Celsius degrees. So given these numbers, you can plug into the Stefan-Boltzmann law, Stefan's law, and E is roughly equal to 1. You do that, you find the total power output of the sun to be 3.8 times 10 to the 26 watts. Well, that's a lot, but that's a number that's kind of too big, it's kind of hard to comprehend. Let's find a number that's closely associated with that, but it has more direct meaning to us, and that is the so-called solar constant. Solar constant. How do you define solar constant? The solar constant is defined as the intensity of the light coming from the sun in the Earth's upper atmosphere. And that is, suppose you are in the Earth's upper atmosphere, you hold a receptor 1 meter by 1 meter in area, facing the sun directly. Okay, how much power do you intercept? That is called a solar constant. Okay, how do you calculate solar constant? Well, let's see here. We typically use this symbol, this little symbol to represent the sun. This is the solar constant. It's defined to be the total power output over the area. And this area, we're talking about Earth to sun. This, it's a huge sphere centered at the sun with a radius between the Earth and the sun. So we're looking at something like this, okay? We're looking at, a sphere about this big, right? Here's the Earth right here, and the sun is over there. And imagine there's a huge sphere centered around the sun with the Earth to sun distance being the radius. And due to symmetry, the power is uniformly distributed over this area. The intensity should be the same. And that is also the intensity that you would receive if you are in the Earth's upper atmosphere. And so you can calculate that by taking the total power output divided by what? By the area of this large sphere, okay, which is 4 pi r squared. This r is the Earth to Sun distance, and that r equals to, otherwise known as 1 astronomical unit, okay, it is 1.5 times 10 to the 11 meters. All these numbers can easily be found online. So you know what P is, you know what R is, and you can find a solar constant. Equals to what? Equals to 1.3 times 10 to the 3 watts per meter squared. Actually, to a more precise calculation yields 1.37. Okay, this is an extremely important number to know. An extremely important number to know. You know what that means? It means that under ideal circumstances, if you take a receptor only 1 meter squared, which is not very big, right? Hold it in your hand, facing the sun directly, how much power can you get from the sun with only such a small area to receive energy from the sun? The amount of energy you get is 1.37 kilowatts. Okay, 1.3 kilowatts. That's about 2 horsepower. 2 horsepower per meter squared. Wow, 2 horsepower. That is enough to run an air conditioner for a medium-sized room, you know, just 1 meter by 1 meter. So what did that tell us? There's plenty of energy coming from the sun, okay? The energy density is really high. There is so much energy we can harness from the sun directly through solar panels and other devices that utilize this energy. So here's a picture of the solar panel. Imagine with a solar panel array, for us to harness the energy from the sun. Of course, we cannot always think of ideal circumstances. You know, there's always, you know, the atmosphere can actually blocks part of the sun, and the angle between the surface of the solar panel may not be ideal. You know, you can think, and that's also the energy conversion between solar energy and electrical energy. It's not nearly 100%. We're talking about maybe around 10% or whatever. But still, okay, we don't get 2 horsepower per meter squared of solar panel. But what if, you know, I multiply this by a factor of 10, right? For every 10 meters squared, which is also not very big, I can get 2 horsepower. That's still quite a lot, 1,400 watts. You know, again, enough to run air conditioner for a medium-sized room. And what if I have a large, you know, not necessarily large, just a conventional size rooftop, and I line it up, you know, I take half of that rooftop and replace it with solar panels, cover it with solar panels, or better yet, I take the entire roof, replace with solar roof, which means roof made of solar panel material. So the entire roof becomes a giant solar panel. You can get a lot of energy, okay, a lot of power out of the sun on a regular day, especially in sunny places like Southern California. Okay, there is really enough energy to run a typical single family home if you use just solar energy on a sunny day. And you may even have enough, not only just enough energy to run your household, you may have the ability to produce extra energy that you can use, and you can sell it back to the grid. Okay, and you can also use that to power your electric vehicle. So, you know, so basically you're not getting any gas to power your car. You're not getting any electricity from the grid. This is green that gets. And it's not just green, it's also abundant because the solar energy is virtually inexhaustible, right? I mean, there's no other energy source can match the abundance of solar energy and its cleanness. So there's so much in this number, the solar constant, so much in this number. Our future of energy consumption really relies on this number. All right, so this is our discussion of conduction, convection, and radiation. And that also concludes chapter 19. And then we're going to move on to the next chapter, in which we're going to take a closer look at the microscopic picture of an ideal gas system.